Our paper is entitled Decentralized Acting and Planning Using Hierarchical Operational Models. And I'm Ruoxi. My collaborators are Sunandita and my advisor, Dr. Now. We're from University of Maryland. Firstly, the objective is for our work is to take a existing system, a acting and planning system, and generalize it into decentralized style. And we'll explain the original system for a little bit, and then we explain how we make it decentralized. So here is the planning and acting system. This is an agent, and it's interacting with the environment. And there are two major components. First, planning component. It's essentially a prediction and search process that searches through the predicted states, and the plans are essentially possible organizations of tasks and actions. Traditionally, the planning component uses descriptive models, for example, PDDL. The descriptive language tells you what the actions will do, or in other words, the next state after you apply this action. And it has this advantage of searching, being able to search a large state space really quickly. And the acting component queries plans from the planning component, and it mainly carries out the actions, but it uses operational models, which means computer programs that tells how to perform these actions, and those actions will be actuated by the execution platform here to interact with the environment. And the planning is online. We do planning and acting. We only act for our certain steps because the environment is changing. We have to replan and act and then replan. However, the descriptive model of the planner is not consistent with the operational model of the actor. So the planner, like this person, only tells what this robot should do, but this robot does not know exactly how operationally how to do that. The solution is this RAE and UPOM system, which is in ICAP's paper conference, and it makes the planner and actor use the same operational model. So what is a operational model? It basically tells you how to perform tasks. A task is, for example, a name, like clean set. So it's making like a Roomba to clean the set of the locations. And there are potentially multiple refinement methods that can address this task or refine this task. And the method is composed of different parts. First, the task that it is associated to, and the body, which is a computer program with any construct. Is a computer program that produces subtasks, commands, and assignments. It's basically doing this greedy technique that always clean the closest location and then do it recursively. And the precondition of this method is omitted here. It is supposed to determine the applicability of the method to current state, but this method is applicable to any state. An example of a command is shown here. So they're like primitive actions, but you have to send the command to the execution platform to execute the action, like actually cleaning the location. So The acting component uses RAE, which stands for Refinement Acting Engine. What it does is basically traversing the refinement tree. Here's the refinement tree or acting tree. Here's the task, tau, and there could be multiple methods that can be used to address this task, to solve this task. And a method has a sequence of actions, subtasks, or assignments, and you have to do them one by one. If a subtask is encountered, you further decompose it. So there is this hierarchy, like a tree. There are different configurations for RAE to choose the methods. You can choose the method arbitrarily, or you can ask a planner to give it better advice on which method to choose. Okay, and here's the planner. It uses the same operational model as the actor does, and it does Monte Carlo rollouts of the model in a simulated environment. So basically, it samples different method choices and action outcomes. So this orange line is one Monte Carlo rollout, and you do them multiple times. And the objective is to maximize some utility, and this could be reward. Then we choose the method with higher utility. Okay, so the main contribution or motivation of our paper is to make the system decentralized. And suppose there are different agents. Each of them have their own local planner and actor and their execution platform. In order to cooperate, they have to communicate with each other. And they don't have access to each other's explicit models. So one does not know exactly how the other agent is going to do what. But one agent might know what the other agent can do, but not exactly how. And there's this partial observability, which means like each agent has their own local observation and local state. And we need some decentralized planning to give them advices on which methods to choose. And here are different types of communication. Agents can communicate their local state information. They can tell each other what they're actively pursuing or their goal. Or they can tell one agent can tell another agent to do this specific task. Or one agent can tell the other agent its current plan over some task. This is used in a decentralized planner, which we'll introduce later. And so the decentralized acting part of our paper is called Dec-RAE. It stands for Decentralized Refinement Acting Engine. It's pretty much similar to RAE, but it supports inter-agent communication, where communication is regarded as an action, and is supposed to be carried out by the execution platform. And Dec-RAE supports task outsourcing. As you can see in the gray block here, the agent I's method M has a subtask that is supposed to be done by some other agent, either J or K. So in the code, in the method body, we say that we outsource this task to either J or K. But which one do we choose? Dec-RAE can choose them randomly, or it can ask a decentralized planner for suggestion, and the decentralized planner is D-UPOM. It's not, again, analogous to UPOM, but it supports coordination among agents in the planning time through communication. Here's an example. So in the planning time, when agent I is choosing from method M and method prime to resolve this task tau, right? And it does one rollout, one Monte Carlo rollout, like the orange line shows, but it has no idea how well agent I or K are gonna resolve task tau 2. So in order to get that estimation, agent I request agent I and K to do their own local D-UPOM planning. They do multiple rollouts and give an estimation of the tau 2's utility. And then agent I knows how to choose from M and M prime. Here is our experimental domain. We have Roombas that can move around and they can pick up the dirt right beneath it, but they cannot sense their locations except for the one that right beneath it. And they have limited time budget. By the way, each command or each action is associated with a time duration. And a drone can fly around and sense the locations of the dirt within a range. And the dirt are randomly generated. Each has a value. The objective is to maximize the score for the team within the limited budget. And the score is the total sum of the value collected from the dirt. Here's our first set of experiment, and each experiment has only one robot, one Roomba, and 15 dirt locations. We tell the Roomba where they are, and there are 5 different Roomba decision strategies. Like they use different methods that I just showed you. And we observe that the Roomba can find the best trajectory or the sequence of the dirt, of the 15 dirt, a subset and their sequence to clean when the agent uses the planner with a lot of planning, or the N means the number of Monte Carlo rollouts. And the second set of experiment tests the communication. So there are 4 Roombas, no drones, and 15 dirt locations. We tell the Roomba team where they are, and they all go and look out and clean those locations. But the Roomba team with communication with each other can perform better because one essentially tells other agents in the team what is actually pursuing to prevent duplication of efforts. The third set of the experiment is on D-UPOM. So we have not had it ready for the DMAP workshop in our paper, but we did it after the workshop submission, both the code implementation and the experiment. So here we have 4 Roombas and 1 drone. And the drone is supposed to survey around the area and locate the dirt and outsource the cleaning task to one of the Roomba. And we observed that the drone with planner enabled, with D-UPOM planner enabled, can make better decision of which Roombas to assign the cleaning task to. It may assign the Roomba that is closest to the center of the dirt. Depending on, it also depends on like the values of the dirt, like if the Roomba can have a trajectory that collects the most value within the budget, will be selected by the drone. Okay, so our contribution is a decentralized version of the acting engine, right? Which supports communication and task outsourcing. And we also have a decentralized planner that use communication to coordinate the planning in the planning phase. And it's also online. And there are some limitations that we are interested in addressing in the future. Firstly, we don't support action synchronization and conflict resolution between different agents. And the communication in D-UPOM only communicates minimum information. In other words, the utility function, the utility value is just one value. But what we can do more is to communicate more information about the plan. And with that information, they can potentially better cooperate with each other, like synchronizing each other's actions like that. And also we want to make our system more resilient, like given that communication is not always perfect and reliable. And that's it. Questions?